This is a continuation of Worksheet 4.5, Concentrations of Solutions. And we're going to be talking about dilution. So you're going to need your notes. And again, you're going to need your highlighter, a pen, and your worksheet. You're going to have to turn to the third page, bottom of the third page. Later on, we're going to determine how to make a dilute solution from a concentrated solution. And the other thing you're going to need that you don't have this time is the last part of the notes. You're going to have to print them out at home. So here's the notes for titrations. Okay, you're going to need these two. But we're first going to start with, make sure you print. Let me back up and say, make sure you print this out beforehand so that you have it to highlight. But first we're going to start with dilution. And you already have these notes, so let's read along. Dilution, the way that we want to think about this is solutions that are routinely in the lab are prepared in concentrated form, and the vocabulary word for that is stock solutions. So stock solutions are routinely in the lab prepared in a concentrated form. For example, hydrochloric acid is purchased as a 12 molarity solution. That would be a stock solution of hydrochloric acid. Now, if you need something of a lower concentration, you would start with your stock solution, 12 molarity, and you would add water. So solutions of lower concentrations can be obtained by adding water. This process is called dilution. For example, you're asked to dilute a stock solution of 1 molarity of copper sulfate to 250 milliliters of 0.1 molarity of copper sulfate. So I want to go over this again because I think it's important with dilution, so you don't get confused, to really dissect each and every word. And so let's just go over it again. This is a word problem, and when you're working on these math problems, take your time. So let's do it. Dilute a stock solution, and the definition of a solution, highlight this, is a homogeneous mixture of two or more substances. And so the solution, stock solution that we're going to be dealing with is a stock solution of copper sulfate. And we are given the molarity, and we have to dilute that stock solution to 250 mils, that's the volume. And remember, when we do the molarity equation, this has to be converted to liters, of 0.1 molarity. That means copper sulfate, the concentration of the dilute solution. Okay, that's what we're aiming to dilute the solution to, this molarity. And copper sulfate is the solute. So we have here on the side that, here's that famous equation that we've been working on. Molarity equals the moles of solute over the volume of solution in liters. Now, one thing that you want to remember at this point, because it's a continuation of what we learned last time, that you can do conversion factors here. Molarity could be written moles over liter, or you can inverse that, liters over moles. Okay, so we learned that there's two conversion factors for molarity. And I also note that I have K. K means that the molarity is unknown. So we have a molarity known, and we have a volume of solution, that another known, but what we do not have as our unknown is moles of solute. Okay, so we're just making note of our knowns and unknowns as we go along here. So here's a note that's very important. When a solvent, and let's highlight what the definition of a solvent is. When solvent, which is a substance present in greatest quantity, in this case is water, is added to dilute a solution, the number of moles of solute, remember what a solute is, it's down here. A solute is other substances in the solution. And when you speak about a solute, you say said to be dissolved in the solvent. So copper sulfate is dissolved in the water. That's how we're going to word that. And the point here, this is very, very important. When solvent, which is water, is added to dilute a solution, the number of moles of solute, in this case up here, it's copper sulfate, remains unchanged. Very, very profound statement, because I actually have it here, and I have all these stars. You want to keep reading this over till you understand it, because this understanding right here is going to help you so much with the mathematical equations. So now what I did is, remember up here I said my unknown, we did not know the moles of copper sulfate from our equation at the top. So now we're going to do the math. We're going to put what we know, which is 0.1 moles of copper sulfate, and we're going to put that over 1 liter of solution. And we get and then we're going to do a conversion factor here. 2.50 liters over 1. And here, the opposite sides cancel. And we do the math. 0.1 times 0.25. And we get 0.025 moles of copper sulfate. Because moles of solute before the dilution equals moles of solute after the dilution. Okay, this reasoning is very important. It actually goes with what I started, the same thing is being said. We use 0.025 moles of copper sulfate, which is the solute, and 1 molarity of copper sulfate to calculate the volume of the concentrated solution that we need to withdraw using a pipette. Okay, so let me just turn this over so you can see. Because moles of solute before dilution equals the moles of solute after dilution, we use 0.0250 moles of copper sulfate, the solute, and 1 molarity of copper sulfate to calculate the volume of the concentrated solution that we need to withdraw using a pipette, and add to a 250 ml volumetric flask. So let's just look at this on page 150. All right, so we have procedure for preparing 250 mils of 0.1 molarity of copper sulfate by dilution of a 1 molarity copper sulfate. A, let's look at the picture. You're going to draw 25 mils of the 1 molarity solution into a pipette. So here's your pipette, and you're drawing up 25 mils, and then you're going to add this 25. You're going to add this to a 250 milliliter volumetric flask. So here's our volumetric flask. Then you're going to add water to dilute the solution to a total volume of 250 milliliters. All right, so now you have the visual of what we're actually trying to do with this math problem. All right, so we know that we just calculated the moles of copper sulfate, and because the moles of solute before dilution is equal to the moles of solute after dilution, then we're able to use this calculation. 0.025 moles of copper sulfate, and we are going to convert that to liters. So we do a conversion here, 1 liter of copper sulfate over 1 mole of copper sulfate, and we get 0.025 liters. Therefore, the dilution is achieved by withdrawing 0.025 liters or 25 milliliters of the 1 molarity solution using a pipette and adding it to a 250 milliliters, this got cut off, 250 milliliter volumetric flask. Now, in my opinion, this whole page right here of dilution is going to take some time and thought. You're really going to have to invest in this so that you understand exactly how to do these problems. So you might want to take a moment, read through it, and really process how to do this. Oh, and then here's our next note on, if you turn the page, it says here that we're going to, when we use a pipette, add it to the 250 milliliter volumetric flask. And then when we do that, we're going to dilute it to a final volume of 250 milliliters. All right, so let's just go back and try to think of a way that we can create some type of visual to understand all that's going on here. And we have to come up with a good strategy to attack a problem like this. And the way that I want to attack it is to go back to this visual that I showed you and remember certain vocabulary, that this was the the copper sulfate stock solution. So this is how you would buy it at the chemistry store, and it would be bought in 1 molarity concentration, but you don't want to use something so strong in your lab because the lab that you're working on is calling for a dilution of 0.1 molarity of copper sulfate. Okay, so here we have our stock solution, and then here we're going to dilute the stock solution by using this pipette. And the question that we need to ask is, how many milliliters do we withdraw and put into the diluted volumetric flask? Okay, so here's what I came up with to help you do the math. And you're going to need a piece of loose leaf paper. And I want you to draw pictures with me. I know how much you guys always love to draw pictures with me in class. But anyway, let's just do this because I think it's going to help you out. All right, so we're going to draw our volumetric flasks, and we need 2 of them. One of them, the one over here, is going to be the stock solution. This one is going to be the 1 molarity of copper sulfate. And I would like for you to put the pipette in there as well, just to know the different types of glassware that you're going to have to use when you actually do the lab. So there's our pipette. Let's label pipette. This is a volumetric flask. By the way, the volumetric flask is calibrated, like we'll put it over here, and there's a mark on it, and it would be calibrated to a certain volume. So we'll say 250 mils because that's what we're looking for. We're going to use a 250 milliliter volumetric flask. Okay, so here's our stock solution, and now our diluted volumetric flask is over here. And they give us some information in the word problem about it. It says here that we're going to dilute a stock solution of 1 molarity, we already put that there, of copper sulfate, and we're diluting it to 250 milliliters of a 0.100 molarity of copper sulfate. Okay, so this is what the molarity is going to be diluted, and this is what we, our stock solution, this is what we need to use a pipette to figure out how much do we draw out of this stock solution and put it in here in order to get to this molarity. All right, so I hope that you understand what we're trying to do, and now we're going to work with our very famous equation. Molarity equals moles of solute over the volume of solution in liters. Okay, now, I hope that you can remember something that I told you on page 17 of the notes, that interconverting molarity, moles, and volume, the definition of molarity, we wrote that out and said it, contains 3 quantities. It contains molarity, moles of solute, and liters of solution. So that means if we have 2 of these quantities, we can solve for the third one, and we do. Where do we have 2 of the quantities? We have 2 of them right here. So we're going to start with the diluted solution of copper sulfate, and we're going to figure out moles, and we're going to put them in here. We're going to figure out moles of copper sulfate. All right, so we did that already earlier, but just let's do it again for fun. Why not? We're going to put down our, first off, this is our X, and the volume of solution, which we want to put into liters, is 250 liters, equals 0.100 moles. And then we're going to multiply to solve for X. That's times 0.250 liters. And we're going to get 0.025 moles of copper sulfate. Okay, so now we successfully figured out the moles of copper sulfate that are in our diluted solution. But we still don't know how many milliliters of the stock solution we need to pull out with the pipette and add in here. That's the question. How much volume do we pull out of the stock solution? All right, so this is where that nifty little profound statement comes in handy, and this visual is why this visual is so brilliant. Because, check it out, our stars and highlighted equality here states that the moles of solute before the dilution is equal to the moles of solute after dilution. Well, what does that mean? That means that 0.025 moles of copper sulfate is going to also be 0.0250 moles of copper sulfate in the concentrated stock solution. So, check it out. We have 2 of our knowns, and as soon as we have 2 knowns, see, remember what I said, the definition of molarity contains 3 quantities. So if you already know the molarity and you know the moles of solute, very easy now, you can just solve for the liters of solution, and then that is the answer that we've been looking for. The volume that needs to be pulled out of the stock solution and added to the diluted volumetric flask. So we're going to do that math. Which is 1 molarity and then 0.0250. So start with the equation. Molarity equals moles of solute over the volume of solution in liters. The molarity, we already know, is 1. And the moles of solute, we just looked at 0.0250 moles. And we want to solve for volume, that's our X. So X comes up here, 0.0250 moles over 1 molarity. And as you can see, you get 0.0250 liters because X is volume. And let me ask you this, because you might be wondering, like, how is she getting liters when there's no liter unit in here? I'm so glad, I hope you were wondering that. I'm so glad that you might have been asking yourself that, because remember, the molarity conversion factor is moles over liters or liters over moles. In this instance, moles over liters, and then when you flip it, liters over moles, moles cancel, get rid of that, and you're left with liters. So that's why the answer is in the unit of liters. So don't be confused about that, because we're always remembering, oh, and then you got to convert that to milliliters. So that equals 1, 2, 3, what did we say that was? 25 mils. All right, so let's go back over here. The volume that needs to be pulled up from the pipette equals 25 mils, and then they need to take the pipette and then drop 25 mils in here, okay? You're gonna drop 25 mils of the stock solution in here, and then so that will only give like that much of the stock solution, and then they fill the rest of it up with water. And there you can see, with this brilliant visual, you totally understand dilution in the way that the solutions of lower concentrations can be obtained by adding water. That's dilution. Okay, so we just showed you there with the visual. So I hope that helps to understand this whole first page of notes. Okay, now, it does seem to get a little bit more complicated. And then it gets easier because we get to this little thing down here, and then I think that it makes life a little bit easier for us. So let's just read 3. In the lab, calculations of this sort are often made very quickly with a simple equation that can be derived by remembering the number of moles. Here we go again, that profound statement. You have to always remember that the number of moles of solute is the same in both the concentrated and the dilute solutions. And you also have to remember that moles is equal to molarity times liters. Moles is equal to molarity times liters. Now, how did we know that? Because it's just a rearrangement of our famous equation that we've been looking at for the past 2 hours. All right, so moles of solute in the concentrated solution equals the moles of solute in the diluted solution. Okay, here's that same thing. We've been saying it over and over. It's like the 5th time you've heard it already. So important. Just let that sink in. And we like this. We like to use this little equation here because it's a really easy way to deal with dilutions. And this is how you should read it. This is capital M, and then that's concentration. So it means this is molarity concentrated stock solution. It is always higher than the molarity of the dilute solution. So let's just look at that. The molarity, right, that's molarity concentrated. So that would be this one in our picture. The molarity concentrated stock solution, which is this, it's always higher than the molarity of the dilute solution. See, look, it is higher. 1 molarity of our concentrated stock solution is higher than 0.1 molarity of our diluted solution. All right. And that you times that by volume. The V here, you have to know what all these symbols are. This volume is going to always be lower than the volume of the diluted solution. So this volume is always going to be lower than the volume of the diluted solution. All right, so that's something that you need to remember. And then M, molarity diluted, this is the molarity of the dilute solution. It is always lower than the molarity of the concentrated stock solution. So I just showed you that. It's always lower. This molarity diluted is always lower than the concentrated molarity. And then we have the volume of the dilute solution. Because the volume is higher upon dilution, the volume of the dilute solution is always larger than the volume of the concentrated solution. So these values, this value is going to be larger than this value. Okay? And now you're going to want to look at this note. The above equation is derived in terms of liters. However, any volume unit can be used as long as the same unit is used on both sides of the equation. This is really important because before you could only plug liters into that molarity equation, but with this equation, you can use milliliters for volume here, but you better use milliliters for the concentrated side on the left side of the equation and milliliters on the right side of the equation for the dilute solution. So just remember that. That's a little note here. And so if we go back to our copper sulfate solution, look at how easy this is. If you plug in, we're going back to this. Let's look at this picture real quick. Pull this out in front of you as we do this. Okay. So now you can see that, let me write it out over top. M, write this out with me actually. MCON concentrated times volume concentrated equals molarity dilute solution times volume dilute solution. So all you have to do is plug it in. So much easier this way, isn't it? So the concentrated, check it out, concentrated is 1 molarity. And remember, we were solving for this. We didn't know it was 25 mils at the time. So this would have been our question mark. This is what we wanted to figure out. But we were given the molarity of the dilute solution, which is right here. And that's 0.100, and then we times it by the volume of the dilute solution. That's 250 mils. So we know now, remember what I said, you can use milliliters in this equation, but your answer is going to be in milliliters when you solve for the volume of the concentrated solution. So basically it's just solving for X. You can call this X if you want. And you end up getting, when you do the math, you end up getting 25 mils, as we saw earlier. Much easier method. It only took 3 little lines as opposed to a whole page of notes. So you can really appreciate that equation. It took me a whole page of notes to do it dimensional analysis, whereas this equation here makes it like it says. It's calculations are made very quickly with this simple equation. Now we're going to do sample exercise 4.14 on page 150, and you're going to also do the practice exercises from page 151. We're going to look at sample exercise 4.14 on page 150, and let's just rewrite the equation that makes this a lot faster. Okay, and it basically says that how many milliliters of a 3 molarity sulfuric acid are needed to make 450 mils of 0.1 molarity of sulfuric acid. So the 3 molarity obviously is the concentrated one because it's higher than the 0.1 molarity, and we know that 3 is concentrated based off of the rule that is stated right here, that the molarity of the concentrated solution is always higher than the molarity of the dilute solution. So we're going to plug in 3 here, and then we're going to solve for X. That's what we're looking for. And the dilute solution, molarity of the dilute solution is 0.10 molarity of sulfuric acid, and 450 milliliters is the volume. So if you do the math, you basically are going to end up getting an answer solving for X of 15 mils. So as you can see, this equation makes these calculations fast and easy. Alright, so that ends our notes, and now we're going to open up to our worksheet, and we're going to fill in the blanks for dilute solution. So it says here, determine how to make a dilute solution from a concentrated solution. Many solutions used in the lab are purchases or made in a concentrated form called stock solutions. From here, scientists perform a dilution to get the concentrations they need. The same basic procedure is followed for every dilution. A small amount of concentrated solution is extracted and put into a separate container. Water is added until the desired volume is obtained. And we learned that the container in our figure 4.18 is a volumetric flask. And the way that they extract in that same figure is through a pipette. How many liters of concentrated hydrochloric acid, 8 molarity, would you need to make 1 liter of a 4 molarity solution? Okay, so we know that this one is the concentrated solution. Because of the molarity being higher than this one. This is the dilute solution. And we also know that we are trying to calculate this in, we're looking for volume. That's the unknown. Alright, and so if we do it the old way, we can visualize again, if we take out a piece of paper, we can visualize exactly what there is when you buy that illustration that I gave you before. I just want to do it one more time. Okay, if we have 2 volumetric flasks, okay, and this one's, we'll call this one the concentrated, and that's the pipette, and we have it concentrated to 8 molarity of hydrochloric acid, and we're looking for the volume. That's our unknown. And what we do know is that we have the dilute solution is 4 molarity hydrochloric acid, and it's 1 liter volume. So remember from the calculations before that we had the definition molarity equals moles of solute over the volume of solution in liters. So if we plug this in, we get 4, and we don't know this moles of solute over the volume, which is 1 liter. And when we solve for X, we get 4. So the moles of solute is 4 moles of solute. And we know because of our notes that I gave you that the moles of solute for the dilute solution is equal to the moles of solute for the concentrated solution. So this also equals 4 moles. And then if you plug this into our equation, molarity equals moles of solute over volume of solution in liters. Molarity is 8. And moles is 4. And we're solving for x. So you do x equals 4 moles divided by 8 molarity. And we get 0.5. And that's liters. 0.5 liters of, so the 0.5 is going to be here, 0.5 liters of an 8 molar solution. We will pull out with the pipette, okay, 0.5 liters, and we're going to add it into the 0.5 liters into the dilute solution and fill it up to 1 liter. That's basically what we're doing there. So, if you were to do the math, you would work it out here, so make sure you do that when you turn it in and you get credit for it. And also add, when you get your answer, 0.5 liters that you write of 8 molar solution, actually extract 0.5 liters of 8 molar solution, and add water until it's at 1 liter. Okay, so that's going to be your answer, but make sure you show your work where I did the math here. Alright, now that's the long way. You can also do it using the simple equation, and that's on the next page. So turn the page, and there is a simple equation that can help you with the dilute calculation, and we're going to write the simple equation again. M concentrated solution times V volume concentrated solution equals M molarity of the dilute solution times V of the dilute solution. Okay, so now it says here that oh, it's actually the same problem from the page before. So the M concentrated was M concentrated here was 8 molarity times the volume, which we didn't know, equals M dilute, which is 4 molarity, times the volume, which was 1 liter. And now you're just going to solve for x. X equals 4 over 8. And then that's where you're going to get x equals 0.5 liters. As you can see, it's this equation. It's so much easier to use than what we did over here. But the reason why I like to show you this is because you have to be able to visualize, and I think these pictures do a good job of visualizing exactly what's happening, how you're taking, when you solve for this volume, you're actually pulling that much of the concentrated solution out, only 0.5 liters, and then you're putting it in only 0.5 liters into the dilute solution and filling the rest of it up with water. So it's just a good visual. What volume? The next. Okay, so let's look at the next one. What volume of concentrated copper chloride is needed to make, and then you're supposed to cross this out, 0.05 liters of, and then you're going to cross this out, a 0.01 molarity solution. So we're going to use the equation here, M concentrated times V concentrated solution. And we're going to get the concentrated solution is, oh, did she change that? She changed this too. I'm looking at Mrs. Nagel's notes. So change this to 0.1 molarity. Okay, so the concentrated solution is, let's write it again, M concentrated times V concentrated equals M dilute times V dilute. And the concentrated one obviously is 0.1 mole. And we're looking for the volume. We don't know that, so we'll call that X equals the dilute, which is 0.01 time molarity times 0.05 liters. So when you solve for X, you know that you're getting it in liters because of that other rule that I told you. How you're allowed to, it's right here. The above equation is derived in terms of liters. Any volume unit can be used as long as the same unit is used on both sides of the equation. Since we're using liters on this side, then X is going to be in liters. And when you do the math, you should get 5 mils. So what does that mean? It means that 5 mils of the concentrated copper sulfate is added to water until it gets to 50 mils. So 0.5 mils concentrated copper sulfate solution, add water until it gets to 50 mils. Actually, when you do the math here, that's converted to 5 mils. The answer is going to actually be 0.005 liters. And then you convert that to 5 milliliters. And you convert 0.05 liters converts to 50 milliliters. Okay. This one you're going to do by yourself. And this one you're going to do by yourself.
It's Gabe here, and we're just gonna talk about chemistry right now. And right now we're gonna see about the
He's actually filming it.
CuSO4 solution. So MCONC means,
it's not NCONC.
that's what it says. I mean 1.00M plus VCONC equals the 100M, 250 ml.
Get out of here now.
25.
Gabriel, now I'm doing something. Now quiet. I got it.